Welcome to EE World. I'm Senior Technical Editor Martin Rowe. As digital data streams increase in speed, frequencies rise, and time per bit shrinks. That leads to signal integrity issues, which get more and more complex each time the data rates increase. Those signals have to travel over a circuit board. How does that circuit board's materials and construction affect the signal integrity of those signals that travel across the board? To learn more, we spoke with Bert Simonovich of LambSim Enterprises. Bert is a designer of high-speed PC boards and backplanes, and he has done a lot of research into how PCB construction, particularly trace roughness and glass weave, impacts the quality of digital signals. Bert has written numerous papers on these topics and presented them at conferences such as DesignCon. At the time of this recording, Bert is a nominee for a DesignCon Engineer of the Year of 2024. Bert, thank you for speaking with EE World. Can you give the viewers an introduction into the physics of PCBs and how their construction affects signal integrity when simulating a design?
To begin, I guess I'm involved with signal integrity, high-speed signal integrity mainly, but along the way, I've come across material properties, impacts on designs. And I've done a lot of my own research on conductor roughness a few years ago earlier, and that was the main focus. But since then, I've realized that the conductor roughness affects not only the loss of the actual metal or the conductors, it also has impact on the dielectric properties of the material. And these dielectric properties are used then to model your design. And if you don't account for them, then typically you may end up with the wrong, not as accurate answer in your simulations. So I kind of put roughness affecting your PCB laminate stuff more at the top of the list because it has an impact on all of that. And then along the way now is the actual dielectric material is anisotropic. It's anisotropic properties, meaning the electric fields react differently in the dielectric depending on the axis that it's being excited with. And the impact there is how the permittivity or dielectric constant is derived or published that board shops use to define your stackup and do the impedance calculations. And depending on the test method used, the decay will be either in plane, what they call, or out of plane. And if they're in plane and you try to use it for transmission line modeling, you'll get the wrong impedance. And when you build the board, it may fail the tolerance mask. So this is the topic I'll be discussing at DesignCon this year. And I've done some research on it, and I've come up with a way to convert between one and the other based on the data sheet. And that's what the presentation will be about. So that's the material properties there. Then at high speed, we start thinking about fiber weave effect. When we have differential pairs connecting serial links. And you can experience fiber weave effect, starts to impact things sort of 10 gig and above type of things. Because the higher you go, the less margin you have in your design. And what fiber weave effect does, it creates a skew between the one trace and the other, like a timing skew. And what that does is, your certain budget, you'd end up with, extra loss potentially in your design with it. So people, they can mitigate that with different techniques. they have like what they call spread weave glass that spreads the actual fibers of fiberglass cloth in the resin. So that helps to mitigate it, to equalize the decay in there. And they also can rotate the artwork when they do the design and different things. So, and then there's issues if you rotate, depending on the angle of rotation, then you can create other effects called the Floquet blotch effect, where you can get tiny little resonances in the insertion loss. So it all ties together how you start looking at it. So that's just general overview of how everything is related.
Does trace surface roughness add impedance to a transmission line, thereby affecting current flow and magnetic fields?
As you mentioned, the copper that gets put down is not perfectly smooth. In fact, they intentionally make it rougher so they get good adhesion to the dielectric material. So in some sense, it's what's good for mechanical bonding and peel strength to keep the traces on the board for rework or everything, goes against signal integrity as we go up in speed. So it effectively, adding roughness increases the loss of your signal, between the two interconnects or your net, basically. And along the way, the roughness itself, it also adds some additional delay to the circuit. Has more of an inductive effect as well. So it could affect some timing. And also if you're doing like RF design, the roughness, not as concerned with the loss there, but it does affect the dielectric, in that perspective. So there's two ways of looking at it. The circuit model, so to speak, where electrons are flowing through conductors. That's what people use in a model, and to a certain point, that's is good enough model. But electromagnetically, it's actually the wave propagation is guided by the transmission line of the copper and the reference planes. And adding roughness starts to impede that that propagation of it. So it acts some delay, but it also absorbs some of the energy as well, and bit of some sort of scattering. So electromagnetically, you're attenuating that signal going through. The old roughness kind of model was, it has like peaks and valleys, and current would go above and below, and it would increase the loss because you make the path longer. That's how people used to think of the roughness. Now you got a longer path, that accounts for the extra loss. But that's not actually how physics works. If that was the case, you'd be violating the physics laws of speed of light. You'd have to go faster to get there. So essentially, roughness is no good for loss. And what we try to do for the higher speeds is to get less rough foil and have different bonding techniques, to get good bonding, yet have a fairly smooth surface in the copper itself now. So that's what we're trying to do when we're getting into the higher speeds. Certainly at above 20 gig, 25 gig, 56 gig, 112, it keeps going on now, as the system's going. Every couple of years, it seems to be pushing higher and higher.
Every time data rates increase, a new physics problem arises. One of those is fiber weave effects. PCBs consist of fiber strands that give them strength. But how do those fiber strands impact signal integrity, particularly in differential signals?
When we fabricate the actual printed circuit board laminate itself, the material, it's made of a mixture of fiberglass woven cloth. So just like your cotton cloth is woven, and it's like a grid affair. Don't know if you can see. And, weaves up and down X and Y. So they call that the warp and the weft or the fill direction. So the weave pattern, because it's like a checkerboard, for lack of anything better, you have glass fibers running X and Y, but you end up with some space between, like resin, like a open space, if you actually looked at it. So when they make the actual laminate, they impregnate that cloth with resin. And they call that pre-impregnated, it's what they call it. And it's partially cured. Now, what they do is they take these pre-preg sheets, there's certain thicknesses, and they can vary. You can put different sheets together to build up your thicknesses for your laminate. And they put copper on each side of these sheets, and they press it under heat and pressure, and it's cured. Okay, so that's the actual, what they call core laminates. It's already cured with copper on it. And then they'll etch the pattern of your circuit on each side of or one side, depending on what it is. And that's fine. Now, when you get a differential pair, there's two traces, that are close together usually, and they're routed together along the surface of the core. Now, remember I said it has a grid pattern of the fibers going X and Y. So if one trace lands on the fibers going X or Y, say it's just going in the X direction, if one trace is landing perfectly on that thing over the entire length, but the other trace now is over mostly of the resin, where the open windows are between those two X fiber traces, like they'll have a pitch. And if your transmission line are not on the same pitch, one trace will be mostly on glass, the other will be mostly over resin. Now, the dielectric constant affects the speed of the signal as it gets propagating down. And if you have two different dielectric constants, because the dielectric constant of glass is higher than the dielectric constant of a resin. So now the positive end of the trace will travel at a slower speed if it's over glass than the resin. And that difference in speed is what we call the skew, if you like, in timing skew. So if you have a differential pair, you have the signal is differential. So that means you got a plus signal and a minus signal traveling down the pair. And if you get one traveling faster than the other, then when it gets to the receiver, they're not perfectly matched. They want to cross at the centers, basically, and that becomes differential. And when there's skew, that's when you get what we call mode conversion from differential signal to a common signal, is the amount of skew. And now having common signal on a differential pair is not good because it would radiate. It's common to both. And that's why they put chokes on and do things. So you try to, not have any kind of skew in your differential pair. And a main contributor of skew is fiber weave effect in the board. So that's why it's an issue, because, the one trace is seeing, the two traces are seeing two different dielectric constants, if you like, and the speeds are different. So what we do is we mitigate that. There's different ways to do it. The easiest is you just, not have perfectly straight traces if you can. If you can meander the traces and don't have them running perfectly straight. Or if you can't, if they have to be straight, then you rotate either the artwork on the board, or you rotate the actual panel when they fabricate the board at the board shop. They can rotate the angle, of the board so that the traces, if they're straight, they will not run exactly parallel now to the actual fiber weave. They'll run on an angle. So you won't get that effect. So that's what people have been doing. Or now they have what they call spread weave glass, where they actually spread the fibers after they weave it. They'll spread it to fill in the areas that were sort of open in the weave, that checkerboard. So they call that spread weave glass. So that'll help.
So by spread weave, do you mean that the weaves, the glass strands,
Yes,
from one pair or one strand to the next, to the next, to the next,
yeah.
the distance between them will vary somewhat deliberately?
Okay, so
What
when
you're
they
referring to?
yes, yeah. So when you weave any cloth, when you do the weave, they call the warp and the weft. So warp is, let's say it's the vertical or the Y direction, and the weft or the fill is the X direction. And then you have different strands, like what they have, the strand here, and then a certain distance later, they have another strand, of course. So between the pitches of the strands, you have the open space. So normally the warp is the ones that's the length of the cloth that gets drawn, and the weft is the stuff, the weave that goes across each time.
Mm-hmm.
So then the weft or the fill, they'll spread normally the fill yarns to fill in that space. The warp ones tend to be, just because it's under tension, they don't tend to spread, but mostly they just spread it out just to fill in that gap between it. So they could spread both, or just the one. Regardless, it's a spread weave. It's to try to make it more homogeneous, if you like, between the two dielectrics.
How does rotating the entire circuit image relative to the grid improve signal integrity in differential pairs?
That introduces another issue, because now if you're rotating your panel, depending on the angle of rotation, it could cause another bit of an issue from signal integrity. And because now when you rotate, these fiber weaves, when they get woven, they go above and below each other. So they have, where they cross is like a knuckle, what we call like a knuckle. And, that's where the X and Y overlap, sort of thing. Now, if you have a straight trace on an angle, eventually that trace is going to cross the knuckles periodically. Okay? And where the knuckles are, that little point knuckle, that has even additional sort of extra decay. So it adds extra capacitance, essentially, in it. So they call that periodic loading of it. So depending on the angle now, you'll get the loading at a different period, sort of thing. And what it really looks like in insertion loss, you get a tiny little resonant blip, very high Q blip. It's not very deep, but it's blip. And if that blip happens to occur at your Nyquist frequency of your bit rate, you could add more loss of that Nyquist frequency, that we look for. And so you have to be cognizant now of the angle. And it's a simple calculation. You can get the warp and the weft pitch from the standards. You know what those pitches are, and you just use like a trigonometry to figure that distance out, and you can work back and you can predict where that resonance will occur, and it works well. And people have done papers on it, and I've experienced it myself recently. Some characterization work. I've seen the blips, and when I work back the math, it happens exactly right where it's supposed to. So it's there. So you just try to make sure that blip is well away from any important frequency that you want. So that would determine any angle of rotation that you would do to mitigate your fiber weave. So that's how they're tied together. So you kind of fix one thing, but you could create another problem if you're not aware of this other part.
Bert, earlier you mentioned stackup. Most complex circuit boards have more than 2 layers. 8, 10, 12 are quite common. How does the stacking of those layers affect signals on the board?
To build a stack up, it's really what it says. I mentioned before how we made the cores with the double-sided copper on it. If you're building a multi-layer board, it's a stack up. You have a series of cores, that you're putting together. But to glue those cores together, double-sided cores together, you still use the prepreg now. So now a stack up is, if you sort of start at the top, you have a top layer, you'll have a prepreg or a core. Let's just call it prepreg. Then you'll have another core, double-sided core, then a prepreg, a double-sided core, and it goes down, down, down to the number of layers that you have. So that in itself is not a big deal, but when you build a stack up, it's important to have symmetry above the center. So whatever is above the center of the stack up has to be the same below as far as the copper thickness, the dielectric thickness needs all to be symmetrical. So typically when we make a stack up, it's an even number of layers. You won't see practically an odd number of layers. It'll be even numbers. Mm-hmm. And that's because they need to maintain the symmetry. What we try to do, it's not totally important, not totally a restriction. What we try to do is to keep on the cores the same thickness of copper on each side. We call it copper weight. In the PCB world is really strange. They often call weight of copper for thickness, like 1/2 ounce copper, 1 ounce copper. It has a certain thickness, and that represents the number of ounces, what the thickness would be of ounces per square foot. So 1/2 ounce of copper is roughly about 0.7 mils thick, type of thing. 1 ounce is 1.4. So you'll see stack ups talk about ounces rather than thicknesses. And when you see ounce, it's roughly that thickness in it. So that's where some confusion happens. How do you get thickness from ounces? But that's where it comes from. So that defines how you actually build the stack up. But you can't go, forever with your thickness, obviously. We run into then, was every board now, you have through-hole drills. They drill through the board so they can mount components or connect layer to layer with the vias. So these drills have a certain size, but now we run into the aspect ratio, what they call board shops, in order to ensure good plating for all the way through the via barrel from top to bottom. They have an aspect ratio. An aspect ratio is the ratio of the drill size or the thickness of the board to the drill size. Like if you have a 10 mil drill, you have 10 to 1, it's like 100 mil type of thickness, right? So it's a ratio of the board thickness to drill size, essentially. And board shops will have a limit what they claim they can work towards. Most board shops will do 10 to 1. That's sort of pretty good. But higher end board shops can go higher, say 15, some maybe 20 to 1, depending on their process. And that'll define the maximum thickness now of your board is the aspect ratio, because you can only have a certain size, your drill size works in. And, that'll impact, your pitch of your BGAs or your your parts that you put on, depending on what the pin patterns are, what can go on there. So it all sort of ties together. So there's a dance between board thickness, how many layers, component pitches, and how you do things. It's it's all works together that way.
Bert Simonovich of Lamsim Enterprises, thank you for explaining how PCB copper roughness, fiber weave effects, and stackup affect the signal integrity of high-speed digital data streams. For EE World, I'm Senior Technical Editor Martin Rowe. Thank you for watching.